Welcome back, focused learners, to another explainer. Today, we're tackling a massive topic. Literally. We are diving into the compaction of soil, looking right under our feet at an invisible engineering process that keeps our modern world from, well, sinking. Seriously, have you ever wondered what keeps our massive structures, like highways, skyscrapers, and earth dams, from simply sinking into the earth? The secret isn't just in the concrete or the steel. It's all about how we prep the ground beneath it. Okay, let's dive right into this. Here is our roadmap for today. We'll start with what soil compaction actually is, and clear up the difference between compaction and consolidation. Then, we'll look at the compaction curve, break down the standard Proctor test, and finally, check out the field compaction methods used on real construction sites.
So let's start with a big framing question. Why don't earth dams and massive highways simply sink under their own weight? You might think soil just naturally settles over time. And hey, 100 years ago, engineers actually used to just pile up earth fills and literally wait years for them to settle before paving over them. But today the answer lies in a highly specific, very deliberate geotechnical process.
To understand how we artificially speed up this stability, let's hit Section 1. What is soil compaction? The mechanical expulsion of air.
Here is the technical definition we are working with. Soil compaction is the process by which soil particles are artificially rearranged and packed together into a state of closer contact by mechanical means to decrease porosity and increase dry density by expelling air only. Now that last part, by expelling air only, is absolutely crucial. We aren't changing the soil particles themselves, right? We are forcefully squeezing out the empty air pockets between them, rather than just letting the ground settle naturally.
And why do we go through all this effort? Well, engineered, compacted, structural earth fills actually make far better foundations than most natural soil formations. It comes down to these three essential benefits. By packing the grains closer together, we increase the shear strength, meaning the soil's ability to resist sliding against itself, and boost the bearing capacity through higher friction. We drastically decrease the soil's tendency to settle over time, and, super importantly for things like earth dams, we create low permeability, meaning water has a much harder time seeping through.
Now, people mix this up with another geotechnical term all the time. So let's look at Section 2, compaction versus consolidation, clearing up the confusion.
Think of a wet sponge. Consolidation is like placing a heavy brick on that sponge and just leaving it there. Over a long period of time, that static weight slowly squeezes the water out. So, consolidation is a slow process that expels pore water under static loading, usually when dealing with clays. Compaction, on the other hand, it's dynamic and mechanical. It's like rapidly smacking that sponge to pack it down. It is a relatively quick process that expels pore air, not water, and engineers use it to actively force the soil into a dense state, right on the spot for things like embankments and earth dams.
But you can't just smash soil together and hope for the best. You have to find the perfect moisture balance. That brings us to Section 3, the compaction curve, finding the sweet spot.
Take a look at the shape of this hyperbolic curve. When soil is bone dry, it's actually really hard to pack it tightly because the friction between the dry particles resists movement. But as you add water, it acts kind of like a lubricant, allowing the particles to easily slide past each other into denser, tighter configurations. That is why the curve climbs up. But watch what happens after the peak. If you keep adding water, that water literally starts taking up the physical space that the soil particles should be occupying. At that point, you aren't compacting soil anymore, you're just making mud, and the dry density absolutely plummets. That exact peak on the curve is what we call the optimum moisture content, or OMC. This is the sweet spot. It's the exact water content where you hit 100% compaction and maximum dry density for a given compactive effort. Finding this peak is the ultimate goal for any structural fill. And once engineers figure out this exact percentage of water, it isn't just a casual suggestion. It becomes the strict blueprint for the entire construction project.
So how do we find that magic number before the bulldozers roll in? That leads us to Section 4, the standard Proctor test, bringing the field into the lab.
To figure out a soil's optimum moisture content, engineers use this specific, standardized lab equipment. This procedure was actually created way back in 1933 and is called the standard Proctor test. Honestly, it's incredible that a test designed nearly a century ago is still the undisputed gold standard today. You've got the standard mold, which has a specific volume, and the standard rammer. And this isn't just any hammer, it weighs exactly 26 newtons and is designed to drop from a highly controlled height of 310 millimeters.
Think of this test like a really aggressive, highly controlled baking recipe.
The processed soil, mixed with a specific amount of water, goes into the mold in 3 equal layers. Each individual layer is compacted with exactly 25 blows from that standard rammer, dropping freely. The technician moves the rammer around each time to perfectly distribute the energy. By doing it this strictly, the test transmits exactly 605 Newton-meters of energy per 1,000 cubic centimeters of soil. Once the 3 layers are compacted, you take off the top collar, trim the extra soil perfectly flat, and weigh the whole thing to get its bulk unit weight. By repeating this at different moisture levels, engineers can perfectly plot out that compaction curve we just looked at.
Okay, we know our optimum moisture content. Now we need to scale up our lab data onto a massive construction site in Section 5, Field Compaction Methods, Scaling Up for Construction.
Out in the field, construction involves placing the earth in layers, spreading it, and mechanically compacting it. The heavy machinery used to pull off this massive industrial effort basically falls into 3 categories: rollers, rammers, and vibrators. While rammers and vibrators definitely have their specific uses, rollers are by far the most commonly used tool for these operations. You've probably seen smooth-wheeled rollers paving roads, or maybe sheep's foot rollers, which are literally called that because their knobby steel studs look exactly like a sheep's foot. And those are perfect for kneading clay-heavy earth fills.
But here's the thing, not all soils are treated the same. As the source material explicitly points out, granular soils are most effectively compacted by vibration. If you are dealing with dry or saturated sands, what we call cohesionless soils, just rolling a heavy drum over them isn't enough. Because of microscopic stresses at the soil-water menisci, which is essentially the surface tension holding the wet grains together, the grains resist packing. High-frequency vibration is the absolute best way to break that tension and shake those sandy grains into their tightest possible arrangement.
So notice how different soil types dictate completely different mechanical approaches. Granular soils, like sand, can actually be compacted adequately in much thicker layers, primarily utilizing that vibratory action we just talked about. But cohesive soils, like heavy, sticky clays, are a totally different story. They have to be laid down in much thinner layers and require aggressive tamping, kneading, and impact principles to force those sticky particles together. If you try to compact clay in a layer that's too thick, the bottom of that layer simply won't reach the required density. No way! And how do they know they've actually done it right? Field control. Engineers absolutely do not just guess. They are constantly testing random locations in the field after the machinery rolls through. They use methods like the core cutter method to extract a perfect cylinder of compacted earth, the sand replacement method for irregular holes, or a proctor needle which measures penetration resistance. These on-the-spot tests ensure that the real-world soil out there under the sun exactly matches the maximum dry unit weight they calculated back in the lab. It is just this incredible synchronization of microscopic physics and massive industrial machinery. So, I'll leave you with this thought. Next time you're cruising down a smooth, perfectly flat highway, ask yourself, how much air had to be mechanically squeezed out of the earth beneath you just to safely pave your way? Thank you so much for joining me on this explainer. Keep asking questions, and I'll see you in the next one.